In one of the previous week's lectures, we talked about self-attention and the transformer architecture, which served as a harbinger for revolutionizing NLP tasks to process text modalities. Since then, the transformer architecture has become a default go-to choice for data across different modalities including text, vision, speech, or even graphs. In this module, we will talk about transformers for computer vision. In particular, we will begin this first lecture with the journey from transformers to vision transformers. Most of this lecture is based on Justin Johnson's Deep Learning for Computer Vision course from the University of Michigan. We are grateful to him for making his materials publicly available. As we already discussed before, transformers revolutionized NLP tasks by introducing a novel architecture based on self-attention mechanisms. This helped in several NLP tasks like machine translation, language understanding, text generation, question answering, named entity recognition, and many more. After the initial transformers work, there have been architectures like BERT, Roberta, DeBerta, T5, and the entire popular GPT series, which represent major contributions in transformer-based models developed for NLP tasks. When we talk about transformers in computer vision, one thing to note is that transformer encoder typically requires a sequence of vectors as input. In language applications, this sequence is just the set of ordered word embeddings that correspond to the tokens within the input. However, how do you do this when your input is an image? Is every pixel a token? If you do that, it blows up memory usage and computations. If you have a 224 cross 224 color image, you would end up needing to store 3 channels RGB into 224 into 224 whole squared, because for every pixel you need to evaluate self-attention with respect to every other pixel, which would total up to a total of about 22 billion parameters for each self-attention calculation. This is simply not sustainable. So then, how do we adapt transformers to computer vision is the first core problem we're going to discuss. This was first proposed in a paper called An Image is Worth 16 into 16 Words, Transformers for Image Recognition at Scale at iClear 2021. What they proposed is, if you consider an image of size 224 cross 224 cross 3, assuming it's an RGB color image, they suggested to break the image into 14 cross 14 patches or small images, each of size 16 cross 16, which means you would now have a total of 196 patches across your image size. Now, each of these input patches can be considered as independent patch tokens, each of shape 3 cross 16 cross 16. Now they project each of these patches into a d-dimensional vector. We will soon talk about what this projection involves. Once this is projected to a d-dimensional vector, they add the positional encoding, which is somewhat similar to the positional encoding that we saw with transformers, but also has some differences which we'll talk about soon. And once we have these patch tokens embedded into a d-dimensional vector and a positional encoding appended to the d-dimensional vector, this is sent to a transformer encoder very similar to the NLP transformer, and the rest of the process is almost the same as the NLP transformer. In NLP tasks like say machine translation, for every word that is given as an input token, you may have approximately an equivalent word as an output token. However, when you are trying to adapt vision transformers for image classification tasks, you only need one output. You don't need 196 output tokens coming out of your transformer decoder. How do you handle this? They proposed the use of one additional token called your classification token, which is also learnable, which also gets updated during your backpropagation. This classification token is also called CLS token. And now at the output, you have a similar classification token that the decoder outputs, and this classification token is projected to a C-dimensional vector of predicted class scores through a softmax operation, which is similar to standard neural network last layers. And one then takes the argmax of the outputs of the linear projection to give your final class prediction through the vision transformer. Putting everything together, your vision transformer looks somewhat like this. Now let's talk about one more level of detail here, which is your position embeddings. In the case of an NLP transformer, the position embeddings are fixed position encodings of the relative position of a word in a sentence. However, in a vision transformer, they proposed to number these patches as say 0, 1, 2, 3, so on and so forth. But they found that simply giving these numbers as additional positional encodings did not really help or did not significantly improve performance. So what they proposed is to have a table-like structure where for each of these positions of patches in your image, they have a corresponding d-dimensional vector, which is now appended to the corresponding patch in your set of 196 patches, and these d-dimensional embeddings that correspond to each position are also learnable and also get updated during backpropagation. Now let's try to compare this with what we saw earlier. We said that if we used a pixel as a token for an image of size 3 cross 224 cross 224, we had 22 billion parameters, while now we have 14 into 14, 196 whole square, because for every 196 patch tokens, you need to have each of the attention with respect to each of the others, which totally adds up to roughly about 38,416 parameters. This is about 150 KB per transformer layer, and see the significant reduction from 22 billion to just 38,000 and odd. Now, one question you could be having in your mind now is, are we now solving computer vision without convolution? The history of computer vision for a large part has always relied on the convolution operation. So have we now managed to address computer vision tasks without convolution? Not really. The linear projection in the input layer is actually a 2D convolution, with stride being the path size itself. Besides that, even the MLP layers in transformers, strictly speaking, are actually 1x1 convolutions. So convolutions are being used, but in a different way in the transformer architecture. Now in this work, they empirically compared the vision transformer to residual networks. They in fact came up with a few different variants of the vision transformer. The B variant, which has 12 layers, the L variant, which has 24 layers, and the H or the huge variant, which has 32 layers. B for base, L for large, and H for huge. Within these, they could also vary the path size from 14x14 to 16x16 or 32x32. Please keep in mind that the smaller the path size yields a bigger model, because you're going to have more number of patches inside a given image. Now they compared this with resnets by deciding what data set to pre-train these models on. The first result on the left, you see a comparison of training these models on the ImageNet dataset, which, as you may know, has 1000 categories with 1.2 million images. And they actually found that residual networks perform better than all of these VIT models in this particular case. However, when the pre-training was improved, they found that when the models were trained on the ImageNet 21K dataset, the resnets and VITs almost were at par, and when the pre-training was improved to the JFT dataset, the JFT 300 million is an internal Google dataset with 300 million labeled images, and when they pre-trained on JFT and then fine-tuned on ImageNet, they found the performance of VITs on ImageNet to outperform resnets. So the conclusion was that VITs do need significant amount of pre-training to outperform resnets. However, when you do that, VITs need significantly lesser training time and are more efficient use of compute than resnets. Why so? One could hypothesize that convolutions are quite costly when compared to simple matrix multiplications that get used in feed-forward networks or MLPs or self-attention computations. This helps in VITs making more efficient use of GPUs. Since the vision transformers were first proposed, there have been other works that have managed to improve the VIT performance in different ways. One of the early improvisations, called How to Train Your VIT, proposed the use of regularization methods like weight decay, stochastic depth, or dropout in the feed-forward layers of the transformer, or using augmentation strategies like mix-up or rand augment, which provides a random augmentation among a set of predefined augmentations. These helped improve the performance of vision transformers. or an improvement called the DEIT, which stands for Data Efficient Image Transformers, proposed the use of knowledge distillation, where a teacher CNN model, typically large, was used as a teacher for training a student VIT model. This is done using the standard cross entropy loss for the student model, as well as a KL divergence loss between the outputs of the student model and the teacher model. Recall that KL divergence measures the divergence between two probability distributions. So you could take the output of the teacher model and the student model as two different probability distributions and compute the KL divergence between them. To do this, this work also introduced a distillation token, which is once again a learnable token provided as input, and the corresponding token at output, the distillation token, is used to match the teacher using KL divergence. And this work, also called DEIT, showed that this idea improved the ImageNet top 1 accuracy from 77.9 to 83.4. In fact, they went even further when they used a higher number of training epochs or higher resolution of images. If one now compared VITs and standard convolutional neural networks, if you take the example of residual networks, one observation we have made through this course is that in CNNs, the resolution typically decreases as you go deeper and deeper inside the neural network, and the number of channels typically increases. This leads to a hierarchical architecture, and the intuition is that such an approach is useful since objects can occur in multiple scales, and you would hopefully discover these objects of different scales in different layers of such an architecture. However, with a VIT, it follows what is called an isotropic architecture, which means each block of a vision transformer has pretty much the same architecture, the same resolution and the same number of channels. So you could ask the question, are we then losing out on hierarchical information? Can we make VITs hierarchical? And this is what was done in a follow-up work called the Swin transformer, which was published in CVPR of 2021. The Swin transformer tried to introduce the notion of different scales or hierarchy in the representation learning of vision transformers. How did they go about this? Given an input image, which is say 3 cross H cross W, 3 being the number of channels for color, H cross W being the actual resolution. This goes through a patch partition and linear embedding, very similar to what we saw with the vision transformer so far. But then, before they do this, they divide the image into 4 cross 4 patches and project to C dimensions. How does this happen? If your image is 3 cross H cross W, they propose breaking the image into 3 cross 4 patches, which is 48 dimensions, 4 into 4, 16 into 3. And now your image becomes 48 cross H cross 4 and W cross 4, because you've divided the entire image into 4 cross 4 patches, and each of these patches now, which are H cross 4, H by 4 cross W by 4, is of 48 dimensions corresponding to 3 cross 4 cross 4. Now they take this 48 cross H by 4 cross W by 4 and project it linearly to to C dimensions. Okay, so this 48 now becomes C, very similar to how we saw the linear projection in your vanilla vision transformer. Now, how does this build on? Once they do this at the first layer, they now merge 2 cross 2 neighborhoods, and patches now effectively become 8 cross 8 in terms of the receptive field, which leads to a H by 8 cross W by 8 overall resolution. How does this work? You had your C cross H by 4 cross W by 4. When you merge 2 cross 2 neighborhoods, this now becomes H by 8 cross W by 8. But because of the merger, each 2 by 2 is now accumulated, and now each of these slots here has 4 C channels, C, and then merging of 2 into 2 leads to 4C. This is now projected linearly to 2C dimensions, and that's how you get 2C cross H by 8 cross W by 8. Now this is then progressively implemented to once again merge 2 by 2 neighborhoods. Now the patches or the original receptive field becomes effectively 16 by 16, and your dimensions at this stage become 4C cross H by 16 cross W by 16, and this is repeated further to get 8C cross H by 32 cross W by 32. Now this gives an effect of learning your image at different scales and hence getting a hierarchical representation of your input. A couple of questions now arise. While the original goal of the vision transformer was to make self-attention computation efficient, by now going back to H cross W grid of tokens, once again your attention matrices are going to be H square W square approximately, which is quadratic in image size. How do you handle this? To handle this, the Swin transformer proposes breaking down the image into M cross M tokens and computing self-attention only inside each window. How does this help? Now, because your image is divided into M cross M tokens, so you have a total of M cross M here, so which means the total number of parameters is going to be M into M, that's M square. Okay. But then for every patch you need to compute self-attention with respect to every other patch, so you're going to have an M square here. But then the size inside each of these tokens is given by H by M into W by M. This hence becomes a total of M square HW, which is linear in image size for self-attention computation. The Swin transformer uses M equals to 7 in their work. The other question you could ask is, because we are restricting self-attention to only within each of those M by M windows, how would you capture long-range relationships within an image? After all, the purpose of self-attention was to capture the context of a particular object with respect to any other part of the image. How do you handle this? To do this, they introduced the notion of a shifted window attention, where the attention windows are progressively changed or shifted in a hierarchical manner that enables interactions between patches across different levels of abstraction. But this captures long-range dependencies while maintaining computational tractability. This is crucial in applications like image classification, object detection, and semantic segmentation. How do they do this? Given any particular layer where you have these M by M tokens or M by M parts, where you compute attention only within each part. So you have a patch here and you have this local window here within which you actually compute your self-attention. They now rotate how these local windows are computed between successive layers of the vision transformer. In one layer, if these are your self-attention window patches, in the next layer, this becomes your self-attention window patches, and then this process keeps repeating. To see it in more totality, you start within a particular transformer layer using layer normalization, then apply your windowed self-attention here, and then that goes to a layer normalization module, then an MLP module, and then in the next transformer layer, you use a shifted window attention, self-attention, and this process is once again repeated between successive blocks of your overall architecture. So one question you could ask here again is, what happens to your positional encoding or embedding? So Swin transformers don't use absolute positional encodings the way vision transformers do. Instead, they encode a relative position between patches using a learnt bias which is included inside your self-attention computation. This B is a learnt bias matrix of dimension m square by m square corresponding to your patches, and this gives you the relative position of your different patches that you're studying within an image. And with this, they actually showed that they could get higher accuracy than vision transformers with distillation, while they could also do this with significantly lesser time in terms of milliseconds per image on a V100 GPU when compared to other vision transformer architectures like DEIT. While we have discussed vision transformers and Swin transformers in this lecture so far, over the last couple of years, both these architectures have become a general purpose backbone for a diverse set of vision tasks, including image classification, object detection, semantic segmentation. In terms of object detection, we have an architecture called the DETR, which we will see in the next lecture. And for segmentation, we have the very popular segment anything, which we will also discuss in this module. Beyond these, CLIP for vision language tasks uses vision transformers, and there have also been other architectures like Swin IR for image restoration. If you're interested more, I'll highly recommend you to also look at the corresponding references for these topics. We will soon get to the details of DETR or transformers for object detection.